Hey everybody, it's Matt. Welcome to week 4. We're going to talk in this video note a little bit about processes, Linux processes, operating system processes, and the context in which they exist, as well as some tools which we can use to look at them and inspect processes, which is a very big part of system administration of a Linux system. So stay tuned, it's going to be a wild ride. So first things first, we have 3 chapters this week in RH 124, the first of our 2 textbooks for this term. So this week we're looking at Chapter 8, Chapter 9, and Chapter 10. Chapter 8 is the topic I'll be talking about in this video, which is monitoring and managing Linux processes. If you look into the next section, Chapter 9, talks about controlling services and daemons, and also finally Chapter 10 is all about configuring and securing SSH. So as I said, this video I'll talk about the idea of a process, a few tools. This is definitely not a replacement for the Red Hat material, so I will reference Red Hat material when I see it, but by and large this video will just be some general overview information about processes that I've taught before in computer science, in the computer science version of this course, and so hopefully it'll be interesting to you and useful, which is what it's all about. Okay, so here's the Red Hat Chapter 8 that deals with processes. So just a quick rundown of the outline. The Red Hat material is going to show you how to list processes, how to control jobs, how to kill processes, how to monitor process activities, and there are some exercises and there's some labs. Now, I'm going to present this a little differently, but I wanted to touch base with Chapter 8 here just because this is what you all will be working from. So the first and foremost order of business here is to talk about what is a process. So the Red Hat material defines it this way. A process is a running instance of a launched executable program consisting of an address space of allocated memory, security properties including ownership, credentials, and privileges, one or more execution threads of program code, and a process state. So these are all attributes of the process. State is an important one. An additional and related idea is the environment of a process. The environment of a process includes local and global variables, a current scheduling context, and allocated system resources such as file descriptors and network ports. So that's kind of the Red Hat definition of a process. I think it works pretty well for our purposes. I will present a little different view next. Okay, let's just jump right into it. So let's talk a little bit about where processes occur in Linux. What is going on here? Okay, it looks like my video software is interfering with my slideshow presentation, so bear with me on this. So a Unix process, in my view, is, you can think of it as the execution of a command. So if you log in, the shell that runs when you log in, the bash shell that runs, that's a process. Linux runs lots of processes in parallel. In fact, the entire activity is a hierarchy of processes, which we'll see. Most commands that you run when you type in a command like df or dd, they'll be run as a process, and we'll look at exactly what that looks like shortly. Now, not every command that you run is going to spawn a new process, but there are a number of built-ins like CD. They're part of the memory resident kernel, and they won't start a new process. So backing up, think about what an operating system is. What is going on? Okay, so what is an operating system? Linux is an operating system, but what is an operating system? And a general definition could be that software, it's a piece of software which runs on hardware, and its purpose is not typical for like a word processor is an application. Snapchat is an application. Those are pieces of software, but the operating system itself is more integrated into the computing environment. It basically manages access to hardware. Right? So software runs on hardware. The operating system is charged with a lot of duties. Managing access to the CPU, managing access to peripherals, managing access to memory, to printers, other devices, I/O devices. We're dealing with complex multi-user systems, multitasking systems, so there needs to be a scheme for managing cooperatively access to all of these wonderful resources that the hardware provides, but in a ordered, structured way such that every process that's running is fairly treated. Has sharing of those resources to multiple programs. So basically, the resource that we're talking about when we're talking about process that's being managed by the operating system, the resource that's being managed by the operating system is the CPU, right? We have multi-users, multiple programs running on our multi-user, multitasking system, and so there needs to be a way to divvy up the time and let every process have a share of that time so that we can have multitasking, parallel type operations. So this brings us to the idea of time sharing. Time sharing is the idea that each process can use system resources, the printer, the file system. Each process can use that for a particular period of time, a brief period of time. So we'll call it the time slice. And so a process gets their time on their time slice, can have access to all these wonderful resources, and then at the end of the time slice, the process would yield their resources, and another process would be swapped in and would have access to the resources. So the Linux kernel manages all of this, and the processes are intended to be as fair as possible and provide each of the processes with an opportunity to run. That's the short version. Now, behind the scenes, processes will queue to run. So a queue is like a line, like at a grocery store where you walk in and you stand in line, right? There's a queue. It has a head of the queue and it has a tail of the queue. Processes and shoppers will go to the queue and get at the tail. They will go at the end of the tail to queue up to run or to shop or to check out. So in this example here, I have a small diagram listed out that shows P4, P1, P8, P2, P7, and P5. Right. So the arrow in this diagram, this diagram here is a queue of processes which are waiting to run. Just hypothetical. So for example, P5 is at the head of this, and it is the active process, and the resources. P5 has access to all the resources for the duration of its time slice, and then afterwards it will release the resources and move behind P4 at the end and get back in the queue, potentially. So this happens so fast that we don't even notice that it happens on a Linux system. That's the kind of the magic of multitasking system is this swapping occurs so rapidly that we don't really, as human beings, notice it because it's awfully fast. The time slices are not really perceptible, or well, they can be perceptible. You'll notice lag sometimes, but in general, it happens so fast. This multitasking happens so fast that we don't even know that it's happening. But this scheme is being implemented to share the resources among all of the processes which are running. Now, a little more esoteric stuff. Most kernels will use the scheme for sharing resources called interrupt-driven priority time sharing. Okay, it's a bunch of $5 words all strung together, but that's just it's an interesting concept, so it's worth getting to know. Interrupt-driven priority time sharing. Let's talk about interrupt-driven priority. So, in a queue, processes have priority, right? So in this example here, P5 has a priority of 10, P7 has a priority of 80, P2 has a priority of 99, P8 110, P1 120, P4 also has 120, right? So P5 is at the head, it has the lowest priority, and in this example, just consider that the lower numbers means a higher priority. Now, that's the concept of priority. Now, the second part of that is interrupt-driven, or event-driven is a better way to conceptualize it. I have here. Sorry, I'm still getting the video layout all here. Here is a state transition diagram, right? A nice tool for showing the situation of when things change, right? So if you're looking at this first circle here, waiting for input, you can pretend that that is the command line, just waiting for input. And if there's no input, or the process is just going to wait for input. That's what it's doing. So that's what's happening here with this little arc arrow here. So in the state waiting for input, no input at all is being looped, and when input arrives, suddenly the process is eligible for the run queue, right? So the user takes an action. The user interface, the user view of this situation is that you're staring at a process like a bash prompt, and it's waiting for input. You take some action. Nothing is happening until you take the action, press enter, and that waiting state is interrupted. This is where the interrupt-driven term comes into play. So it's interrupted. This process stops waiting and is placed on the queue to run and read the input. Okay, so that's sort of behind the scenes. But the basics here are every process has a priority. Every process can be interrupted, either to cause execution to begin or to cause execution to end. And every process must share resources with other processes. And ultimately, every process spends most of its lifetime waiting to run, even though it seems that they're all running concurrently. Most of the processes just sort of sit around waiting to run. Now, so a higher concept here is the task of scheduling, the task of determining what processes will run, when they will run, and making that happen is called scheduling. So the purpose, and this is a software component that runs behind the scenes, and its job is to select at any given time what's the most, quote, deserving process to run in terms of priority and other factors. So there's this piece of software that's built into the operating system, and that's its job, is to decide what happens next, who gets the time slice, who gets the next time slice. So when we talk about scheduling, there's two main operations. To create the run queue is a process called selection, and to allow another process to use the CPU is called swapping. So the only runnable processes In selection, the candidate processes are the runnable processes. Non-runnable processes are not eligible for selection. So the scheduler looks at policy, at priority. There's a counter on each process that determines how long it's already run. So if it hasn't had much CPU time on that counter, it may select that process because it needs more time to run. So once the selection is made, there's the operation of swapping. And that goal is to take the process that's currently has the CPU and pack it up, put it away, and load in a new process. That's a swap. So what happens in that point, this is kind of the more interesting one to me. The current process that's running is suspended. All of the context information, the environment, the data of the current process is packed up and stored, and the new information, context, environment of the new process is going to be loaded into memory, and then the CPU is granted to the new process, and the new process wakes up, looks around, it has its last known state available to it. The process doesn't know any differently, and on it goes. Now, when you swap out, or when the scheduler swaps out a process, you have a swap file, virtual memory, or a paging file, which is an area typically on disk. Sometimes it's in memory to make it faster. And that's where these processes go. That's where they're saved. When I say that the data is saved out, it is actually paged out to virtual memory. So an interesting trivia fact about this is that most processes spend most of their existence in the swap file rather than running actively. So the textbook differs from this version here. So state. Every process has a state. And this is an overly simplified diagram here, but you can think of 4 values. Look at the Red Hat material. In fact, I may pull that up next to show you the difference between my simplification and oh, looks like my video got reset. Okay, hang on, let me fix that. Okay, fixed sort of. Wasn't adding a whole lot having my video there, so. States. So red light, green light, yellow light. Let's just talk about the normal runtime case. Process can be running, right? So the process is either in queue or it's actively running. The process can be waiting, and there are different sub-states of waiting, but basically it's not in the queue, it's waiting to run. A process can be stopped. The process has been flagged as non-runnable by some other process, the scheduler, for example, or the user ends the process or stops it, suspends it. We'll see how to do that. And then finally, there's this cool state called zombie, which is basically kind of an error state. It's a state that every process is going to move through as it ends, as it exits. It'll shortly be a zombie as it's being torn down. So, okay, so Chapter 8 in the Red Hat Academy textbook shows us that it's not quite as simple as the way I sketched it out. I had 4 convenient categories, and the Chapter 8, this table 8.1, right after this overly complex diagram that I'm going to skip because I have my own diagram to show you in a moment, but have a look at this table 8.1 in the Chapter 8 Linux process states. It has its own categories, 1, 2, 3, 4 categories still. However, it's a little more technical than the red light, green light that I just showed. The state running is defined as it's either executing or waiting to run, as I had mentioned. Sleeping actually has a number of substates. The task may be interruptible when it's sleeping. It may be not. It may not be interruptible when it's sleeping. It may be killable when it's sleeping, and it may be just sort of idle. So these flags here will give you an indication in the instrumentation that we can use to look at processes of what kind of state you're dealing with, right? So you see a D, you know that it's a sleeping task that's not interruptible. And it's just this kind of cryptic sort of codes that are in here. Stopped has an additional one flag, two different substates, that it's stopped, that is suspended, which is something the user can do. We'll see that in a moment. Or it's being debugged, like with a debugger. And then zombie, we have an exit zombie. I mentioned that a process can move through this state where it's tearing down. So as it's exiting, it becomes an exit zombie. And then when the parent process cleans up, or reaps, I love that term, reaps the exiting child process, then it's released completely. So you'll never see, according to Red Hat Academy, exit dead, but sometimes you see zombie processes when there's been an error, and it is not a good idea to kill the process. So the operating system places it into a zombie state as well. So this is kind of abstract. Let's take a look at a tool or two. Okay, shown here is a terminal that I've opened onto my server, and this is the top command, T-O-P. I typed T-O-P, I pressed enter, and lo and behold, I got this instrumentation which has an update interval. What this is showing us is the top processes and different metrics about them. So I don't want to spend too much time on this. It's documented pretty well in the module. But just sort of a quick overview. The top five, the header here, the top 5 lines have some interesting information about the system overall, and then the rest of the screen is a changing list of processes which are running, and the top part of this comes from, these are the top N processes by time that that are running on the system, or in some cases not running, right? So the percent CPU here, see how that is a descending value, percent CPU, which is, oh, my mouse cursor isn't showing. That's too bad. So it's like the 1, 2, 3, 4, 5, 6, 7, 8, the ninth column over here. Percent CPU. Notice that that's an ordered list, and so we're seeing the top N by CPU time. One other thing I want to call your attention to is processes have a number, a process ID. So PID is what you can refer to it as, and it has a number of statistics here that are, or a number of properties here that are listed out. But the most interesting, other than the PID, the most interesting thing here is what's the name of the command that's been run. Now I have a lot of windowing desktop stuff running on this machine, so there's going to be a lot of swap out and a lot of activity, and so that's what's happening here. But the top command is actually running, and it's at the top of my list here because it is quite active. Okay, so more about top later. Okay, so let's quickly talk about two operations that are involved in the life of a process in Linux. The the the, uh, the terms are fork and exec, and these are system calls. You will never, unless you're programming, actually issue a fork or an exec function call. Unless you're programming, you might, but just be aware that these things are happening. So the basic process, the basic workflow that happens when you enter a command is that the shell will fork is the best way to say it. So what this means is it will create a child process. So you're at bash, you enter a command, and the bash shell that's running actually has a process identifier, right? Bash itself is a process. As I mentioned, when you log in, it starts an instance of bash, and that's your login shell. That process that's hosting bash is a process that has a PID, a process identifier. So in the example on screen, the PID is 1000, and that's the shell, and you enter a command. In this case, it's a ps3 command. And so what happens is that the two processes are, well, hang on. You enter the command in the shell, PID 1000, and then it creates a child process, which is another process that doesn't contain anything yet. It also copies some things. It copies the environment when it creates a new process as part of the fork operation. And the new process, the child process, has a process identifier. In this case, I called it 1001, but it could be anything. The numbers are recycled, so don't assume anything by the value. It's just easier to see in this example that PID 1000 was the bash shell where you ran the command, and PID 1001 is the forked process which is running the command. So after the fork, the two processes are identical, except for a few things like the process identifier, the parent process identifier, which is another piece of data that you'll see, that indicates that there's a hierarchy. The 1000 process created a 1001 process in this example. They have different process identifiers. The original is the parent process of the new process, and the new process is the child process of the original process. So, there you have the basic fork. Now, the next operation that you'll hear is exec. So after the fork happens, the original shell goes to sleep, right? So in our example, process 1000 has gone to sleep, and after the fork has occurred, the new process attempts to exec the command, and if it's a binary, an executable, then the exec will succeed, and it will load the image into the subshell, or the sub process here, and it will run it. That's if it's a binary program. Now, if it's not a binary program, exec will fail, and the command is assumed to be a script, and the shell will take input from the file if it can find it, but that's a totally different operation. The exec occurs with binary files. So, for example, a command that has a binary executable that's run is a perfect example of this. The exec will succeed, and it will run it. Okay, so after the subprocess completes, the subshell will close, and control will return to the original shell, which will then interpret any exit code from the subshell, and it will prompt for another command. So that is fork and exec. Now that's pretty simple invocation of a command. So here's a more complicated situation, a background case. Whoops, hang on. Background case. Okay, so if you start a command, and I haven't shown you this yet, but it's demoed in the Red Hat material. If you start a command in the background, that is, you type the name of a command, you put the ampersand at the end of it. What this says is run this command, but create a new process and then return back to the original shell. So that's what's happening in this case. So if you start a process in the background using this ampersand, so I'm looking at the diagram here. Again, we start from PID 1000. We launch a command in the background. So it forks, but it does not sleep after the fork. Instead, it spawns a new subshell and then reports the job number and process identifier of the new process and prompts for another command. So in the diagram here at left here, the 1000 forks the 1001. It's in the background. It has a job number, and it immediately returns back to PID 1000 without waiting for PID 1001 to finish. So this looks like on screen you'll get a job number, and along with the PID for the new process. So you can kind of see it here in the graphic. Okay, so now let's talk about job control. So this is where we start actually controlling processes. The way we've been doing it so far is you run the process forks and execs, and whatever happens, happens. But this idea of putting something in the background, which we just saw, by putting the ampersand at the end of the command, suddenly gives us the ability to start creating processes willy-nilly, right? We can stack up as many, well, there is a practical limit, sometimes imposed by the system administration. You can stack up jobs, right? So you can have processes in the background. Maybe one is doing a network search. Maybe another is optimizing a database. It can be anything that you can type at the command line. So the idea of job control, I will say, is a bash specific idea. Let me get my ugly mug off of the screen here so that we can see the idea of foreground and backgrounds. Now, disregard the chapter reference here. This is an old presentation, but Linux is Linux. It's still going to work. So the banner here is out of date. Now, here's an example. If I type ls-l and then I pipe it to the line printer command and I put it in the background using the ampersand, which is shown here in red, it goes off, it does its fork and exec, and it comes back with the job number and the PID for the new child process, right? So that's kind of the typical interaction with putting something into the background with the control character. You'll get the job number, which is in brackets, and you'll get the PID, which is the process identifier. So again, this is a bash idea. Processes are somewhat related to jobs, but job is kind of the job control facility of bash. So you can think of a job as a process that's running a pipeline, which itself may be a simple command, just one command. So it's a distinction that needs to be made, but sometimes I will use the term job when I mean process, or I'll use them interchangeably, but formally, a process and a job are different things, and job control is what we're talking about now, and it's really kind of a bash idea, found in the bash shell with maybe different controllers in other types of shell. So this terminology applies to bash, job. Okay, onward. So if I want to view the jobs that I have in my background, in this example I have used the jobs keyword. I have a rather long prompt here, Matthew MacNaughton at SYCC UXAS01, but that's a prompt. It's just not our Red Hat image. So if I type jobs, and if I have anything in the background, or if I've used Control-Z to stop or suspend a job, or a running process, I'll get a list, right? I type jobs, I get a list. I get a list with the job number. I get a list of the state of the job, not the same thing as state of a process. State of a job in this example is stopped, and then the name of the command. So I've got in this list a vim command, vim new file or vi new file is what's being shown here. So I have one job, it's stopped, and I'm at a prompt so I can type jobs and view the list of jobs that are in that play here for me. You can create jobs in parallel. That's all very interesting. Simply chain together the ampersands, right? Command 1, command 2, command 3, and you can create them in parallel. You can use the pipe command, the or in this case, to create an additional job. So you see how in the first 3 commands here prior to the pipe, those are all one job, and then after the pipe and another ampersand, that's a separate job. So in this case, down here I use the date command, and then I put that in the background, and then I use the uname command, and I put that in the background. Every time there's an ampersand, it becomes a job. Right? So in this example, command 3 piped to command 3 piped to command 4 at the end of this example up here. That whole pipeline, right? There's 2 commands in that example. Command 3 piped to command 4, and then an ampersand. So that pipeline is a job containing 2 commands, if that makes any sense. Okay. So anyway, that's the point is that's what jobs will report when you launch them in the background and when you use the jobs command. Another thing that you'll see in the text is the kill command, which is an interesting and sort of unfortunately named command. The way to stop a job that's running is to use the kill command. Now, ultimately, the kill command is nothing more than a way to send a signal to a process. Well, that's a lot to get your head around. Let's see here. Do I have my camera back? Yes, I do. Okay, let's get our head around this. So I have a process out there in the system being managed by the scheduler, and it's maybe running, maybe not. It has a state, and it's part of a job. So I want to kill the job, so I'll use the kill command. And it has a couple of syntaxes which are shown here in this little tan box, where it says the kill command can use the job number or the PID, right? So the syntax is pretty straightforward. Type the word kill and then a % and the job number, if you want to kill by job number, or type kill and then the process identifier, the PID, without an ampersand. Not an ampersand, pardon me, a percentile sign, right? So percentile job number, no percentile PID. Either way, it's going to terminate the process, right? So I just as an aside, I mentioned it was it was not named well, the kill command. If you dig into the manual for the kill command, it's a way to send signals from one process to another. And the kill signal is only one of many signals that you can send from process to process. Signaling is sort of a rudimentary inter-process communication facility that's in Linux. Signals are basically a value, an integer value that maps to a particular command or signal, really. I think command is probably not a good term for that. So if you look at the kill command man page, you'll see all of the signals that it can generate and all of the ways that you can send signals to other processes. But in this case, the kill command sends the kill signal to a process. that in our case has been put in the background in this example, and that's how it works. Okay, so I have a metaphor for you guys. Let me put the camera up as I explain this. So you know how in Windows operating systems or windowed operating systems, there's the concept of the active window, right? I may have a word processor open, a browser open, maybe a text editor open, and whatever I click on, whatever window I make active, receives the input, right, and responds to the input. So you can kind of see how the whole hierarchical process thing is a perfect way to implement a windowing system. It's just that there are processes, and when you start the process, you might have a window displayed rather than output on a command line. So frame that in your mind. There is a analog. In the Windows world or the windowed world, there is the notion of an active window. Okay, so I just kind of showed you that in the process tree that you create or can create, you can have multiple jobs stacked up. They may be running, but only one of them is going to be active at a time. And in the Linux world, the job control world, the bash job world, the active job is called the foreground. It's just a new term. The foreground job is going to be receiving input from standard in and writing output to standard out. Not in any suspended state, not in any idle state. It's active. So that's the foreground process. The background processes are not receiving input from the default standard input, the keyboard, but they may be active in the background. It doesn't necessarily mean that the job is suspended in the background. It can be running, right? You might have a long-running query or a print job, like that last line printer example. It wants to run in the background, but the important thing to keep in mind is that while it's in the background, you're not going to be able to type and get anything to that program. It needs to be in the foreground first in order to get it to be receiving standard input from the program. So how do you get the job in the foreground? So that's what this slide is about. So we created a new command. We used the ampersand character at the end of our command to put it in the background. Okay? So in order to, when I type jobs, maybe I did that 5 times, and I have 5 jobs listed in my jobs list. So in order to put a background job in the foreground, right, so that I can start working with it, there's a command you can type, FG, and then the job number to run the job in the background. To bring a background to the foreground, you can use FG. In order to run a job in the background, put a ampersand at the end of the command line, which we've seen, right? So that's a way you can spin off multiple processes and then control them at the command line, which one is receiving input and generating output, which is the foreground application. So FG command for that. And then if I've got a foreground job, one thing that you'll frequently maybe discover by accident is that the Control-Z key combination will take the foreground job and will put it in the background. I typically, when I'm using Vim, discover this. Happily typing away, and somehow I hit Control-Z and I'm looking at a bash prompt and wondering where my document went and what's happened. So when that happens to me in Vim, I just type FG and typically it puts me right back where I thought I was. Okay, so to suspend the foreground, hit Control-Z, and then if I want to put that in the background to run, right? So Control Z suspends it. If I look at the jobs, it'll say that it's suspended. And if I want to put it in the background and make it run, I can use the BG and then the percent job number, and that will make it run active in the background. And then, as we've seen, to end the command, use the kill command. Okay, so that's basic job control. Let's see, what else is there? Anything else? No, that's basic job control. So let's see here. What do we want to talk about next? Okay, so now we'll get practical. So you'll have some labs in the Red Hat material that covers this as well. There are some commands that you can use for working with processes. So I'm gonna cover just a couple of them here. Oh, hello. I get rid of this video because I think my fourth one is not being shown. Surely. Okay. So here's some practical information after a whole bunch of theory for, oh my gosh, 45 minutes. Jobs, which I just showed you, then top, which I briefly showed you, and then a couple more, PS tree and PS. So let's just, and I'm not going to do live demos for this. This is just all sort of up here on the screen. So looking at top, I showed you this updating list of the top programs. This is a continuously updating list. It has parameters. You can customize what attributes are being shown. And just real quickly do a run through. The first top line basically gives you system uptime, number of users on the system. This is for multi-user systems. The 1, 3, and 5 minute load average, that is an overall measure of how busy the system is. Then after that, on the second line on top, we have how many tasks are running, what state they're in. Some of them are stopped, some of them are zombie. Yeah. Well, you may see two running at a time, right? If you have more than here where it says one running on line 2 here, the second piece of information, you might see more than two, and that doesn't contradict the one at a time picture that I just showed you of what processes and process swap out is all about. But it just means you've got multiple cores, right? So you can see more than one running at a time. It's not going to be it's not as simple when you get to multi-core or multi-processing architectures. So anyhow, and then after, let's see, the next 3 lines are mainly memory and swap file data for, and then CPU data as well. And then finally we have what's notably called the pig list, which basically it's pig because these are piggies. These are the top consuming processes on the system, and they are ordered by descending CPU utilization, as I mentioned before, and you can use this to determine any process that's causing the system to run slowly. So multi-user systems, I've been in a shop where, you know, I fire off 3 different processes, suddenly everything grinds to a halt and other users are complaining about not having a responsive system, and so I or a system administrator can use the top command and get a list out of what the top pigs are, the top consuming, greedy, possibly runaway processes, where that's something of diagnostic importance. I want to know what the top process is so I can kill it, right? Okay. So it's kind of fun. You have a refresh interval. The pig list changes every now and then, and it's kind of interesting to see the system at work. The Windows system has a process manager, process monitor. This is sort of the text version of that. So there are useful options. You can, as I said, control the update frequency, show user-owned process, show stats for indicated bit number. None of this probably is going to be on the Red Hat quizzes, so this is all just for your info. Next command is pstree, which is kind of interesting. If you go and you type pstree, it will show you parent and child processes somewhat visually on your system. So it's interesting here. If I type pstree, I'll get something that looks very much like this diagram, this ASCII tree at the right here. So the root node is called system D. It is in parentheses shown in this example with process identifier 1, which is interesting. System D is the root. It's the first process that's loaded in the stable system, and then everything is basically instantiated by system D, and so it has no parent. And system D in this system is the only process that can say it has no parent. Everything else has a parent ID of 1 or a descendant of 1. So anyhow, a couple of options you can try. You can try P and U and see what effect that has. Yeah, P will show process IDs and U will show user IDs, so you can kind of customize what information is available here. Okay, so what you have just seen is that processes in Linux are hierarchical in reality, much like a file system is hierarchical, right? You have a root node and you have descendant nodes, and we've taken a pretty decent in-depth look of how that gets built. Now, the book goes on and talks about, in the chapter after this, a daemon. So a daemon is a program that is intended to be a long-running service that runs in the background. By convention, the programs that are daemons or intended to be run as daemons have a D at the end of the name in Linux. So there are examples of this here. There's well, sometimes they just flat spell out the word daemon, okay? So accounts daemon is the second node off of system D here on this example. But some of the other entries in this tree there's a Bluetooth D. So there's a process running as a daemon that has something to do with Bluetooth here in this example. So yeah, so I'm not going to cover daemons much in this example. In this video, I just wanted to call it out because it is a concept that is introduced in the next Red Hat chapter. Okay, so finally, PS. Oh, I love PS and I hate PS. PS is a way to show process status, right? PS, and then there are options, and then there is potentially a list of processes I want to inspect. But if I just type PS, I'll get an output that looks kind of like what's shown here. PS, and then four columns of information. So I have PID, terminal type, time, and command. So the process identifier, we know what that is. Terminal type is, well, in this case, it's going to be the identifier used to identify the terminal that I'm connected on, right? My login shell has this terminal connection, and so that string identifies it within the terminals. It's a holdover from days gone by when there were terminals. So anyway, PTS22 is mine, is my terminal, and then time indicates how much time slice has been used by this process, and then the command is the actual command, or the actual process that is, the command which the process is running. Okay, so that is just if I type PS without any options, right? I get all this interesting information that is essentially my processes and specifically those which have this terminal, um, which have a terminal. So it's interesting if you look at the command column here, the PS and the bash are the only two commands that are being run. Bash is being run as a program in a process, but that's what's generating the prompt and listening to anything that I type, right? That's bash. So that's why it shows up as an item in this list. PS is the command that I just ran. It's a little bit of, it's kind of like you're staring in the mirror here. At the time that this list was compiled, at the nanosecond that this list was generated, PS was actually an active process, right? So it reports it out, returns me to the calling shell, I get my prompt back, and so PS, we just kind of know, is not an active command, but it was at the point that PS was generating this list. Okay, so the thing about the PS command is that it has a lot of masters to serve. It's a hodgepodge of, let me put my camera back up here because I'm being contemplative. It's a hodgepodge of parameter support. So you'll have dash supporting one family of PS lineage in the source evolution, right? So we're talking about traditional Unix, and read the manual. My point is that the options are somewhat complicated and confusing because there's overlap in some of the options in the different, quote, standards that they're trying to support. So PS is kind of, the options are a mess, and it's because it's trying to be all things to all people. So just a warning, I'll let you run with it and discover all of that yourself. I think I'm about done here. We're coming up on an hour for this video note. But all that aside, you know, I'm just telling you there's going to be some confusion and ambiguity if you try to make sense of the options in PS. But one thing you can do, I'll come back here. There's a there is a way to specify exactly what you want to see in that list of columns. And, you know, as a developer, I would almost go there first to use the syntax, which is to basically give it a list of commands. So you can read about that. I'm not going to go into it here. But some useful options are the dash uppercase A. That will list all processes, same as lowercase e. So you can see here's two versions of the options that list all processes, but there's A, uppercase A, and there's lowercase e. And that's because these standards are for backward compatibility with other standards. Anyhow, dash L, we just saw an example of that. We'll give you a little bit more information. So there's an example here. The dash L will list the state. There's the state here, the any flags, right? So we saw the flags earlier. There's a state here. We saw the states and we saw the codes for the states. That's in your book. The user ID, who is the user ID, the effective user ID of the process, the PID for the process, the parent PID for the process. C is the CPU scheduling information, not real important. Scheduling priority, right? So here's the priority for the process. It's 80 in this case. The priority modification set by the nice level. Nice is an interesting configuration that you can put on a process that kind of sets how cranky it is when it tries to get rescheduled. Interesting read, but I'm not going into it here. The memory address of the process is given here with the L command, with the L option. Size of the memory address of the event process that it's waiting on. Doesn't make any sense to me, but there it is. WChan has a wait value in line 1 and dash here. How much time slice it's used, how much CPU has been used in the time, and then the actual command. So PS no options, 4 columns, PS-L 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. More than 4 options. Okay. Alrighty then. So I think that is actually a wrap for me. What I presented is very different from what the Red Hat is presenting. Read the Red Hat. What I've just presented is kind of more conceptual. The interesting thing is this is not just Linux. This is an operating system concept. You'll see it at work on Windows. There are process identifiers in Windows. There are commands that you can use to list processes in Windows. Same in Mac OS and other operating systems. It's a very fundamental operating system concept. So the concepts that you learn in the last hour of watching me ramble are not wasted concepts. And maybe as you're reading through the Red Hat stuff, it'll give you a little more framework for understanding, which is what we're about here at Portland Community College. Okay, so thank you very much for your time and attention. I hope you made it all the way through this and it wasn't too much of a labyrinth of ideas. Have an excellent day, and I'll see you in the next note.